So today we are on lecture EE341 microelectronics. So last time what we did, we talked about phase margin, and also we saw that okay, how we can find the phase from the body plot, and we talked a bit about frequency compensation. So we'll continue from the point of frequency compensation. So this is somehow we concluded last time about the phase margin, and we started about the frequency compensation. So we are still on chapter 12 or section 12.8 of Fundamental of Microelectronics by Behzad Razavi. So the important thing which we talked in the phase margin, that first, for a stable system, we want the phase crossover frequency to be bigger than gain crossover frequency. And then for the phase margin, we concluded that phase margin is equal to angle of the gain crossover frequency plus 180 degree, and gain crossover frequency of what? Of loop gain. I got multiple queries where you have some confusion regarding these fundamental points, and I want to reiterate again in the first page. So make sure you just go through again these concepts. They're again pretty much fundamental, and again, if you need some further illustration, make sure, but this need to be clarified at this stage. So if we have this one input, a feedback system, that is generic for any feedback system. Somewhere the terminologies can be a little bit different, but in general, the concept should remain the same. So if this is a closed loop system, which it is, so if it's a closed loop system, so the gain of closed loop system y over x. So this is, whenever I'm saying y over x, it means closed loop gain, okay, between input and output. So closed loop gain will be y over x. If somebody says what is A, this is means open loop gain. And if somebody says what is K, this is feedback gain. You can say it's a feedback gain. Is now another thing which you all K times A, which we have multiple times talked, also the is known as loop gain. And loop gain is very much important explicitly in the stability of system. Why? If we just write this y over x, it comes out to be that stability issue comes in the closed loop, especially in the negative feedback, and we want negative feedback with system positive feedback की तरह act करना ना start हो जाए, meaning वो unstable nowadays. So this is the relation for the closed loop system. In this relation, if you see this green which I'm highlighting is a loop gain. If this loop gain becomes -1, this means the system starts becoming oscillating, or will be or greater than equal to -1. Yeah, less than equal to -1 ho jaye in reality. So what's going to happen? Your system will become unstable. So this is a condition for ultimately stability, where we say that, okay, the phase margin should be greater than the phase crossover frequency should be greater than gain crossover frequency. But then in the last lecture, we said we don't want the system to be exactly at that point, because the system will have oscillated in nature, or it will have some high ripples, and then it will die down. We don't want these two relations. We want to have like a relation, something like this. So it stabilizes very quickly. So for that, we need to have some phase margin, and for that phase margin, That's why we want the gain crossover frequency of loop gain, meaning Ka. So यहाँ Ka का आपने देखना है. Whenever you want to talk about the stability, you have to bring the loop gain in the equation. So loop gain का आप gain crossover frequency देखेंगे plus 180 degree, and that will be equivalent to your phase margin. Good phase margin, just I mentioned, it's like 45 to 60 degree होता है, but that will be provided, or अगर नहीं होगा तो you can select based on this number. Another thing which I felt there was a confusion. Let me reiterate again. So another thing which was confusing was the something in the problem 4 basically of assignment. So in the problem 4, what was given to you was closed loop gain, meaning if I just talk about the previous equation, it was given y by x, value was given as equal to 10. And then it was provided to you, you need to find the stability or whatever, if you want to stability or phase margin of the system. So if you want to find these two things, how you should proceed towards the thing. So that was somehow, let me open the problem. So you were asked to find the phase margin rather, not the stability. Okay. So you were asked to find the stability of the system. And A was given to you as 10 raised to power 3 by 1 plus s by 10 raised to power 4 divided by 1 plus 10 raised to power 7. So the otherwise the system is in normalized form. We don't have to do anything, but this A of s is a open loop gain. So it's an open loop gain for us. But for the phase margin, we need loop gain. So for loop gain, what we need? We need K times AS. So from where to get this K, because that is not provided in journal. But one thing we know that if this is a closed loop gain, the closed loop gain, if this is H of S, if I say, so the closed loop gain is ultimately at omega is equal to 0, at S is equal to 0, or at a DC value, the closed loop gain H of S at S is equal to 0 is equal to 1 over K. How? We all know this thing. If this is H of S, we have A of S divided by 1 plus K A of S. One thing we can directly put S is equal to 0 and we can figure it out. Let's say if S is equal to 0. And just putting it, I will show you at the end of a lecture a little bit brief explanation about this concept. So normally when we put this thing A of 0, meaning gain of a system at a 0 value, we take it as a very big value. So infinity we normally take. So when this number is going to be infinity at A of 0, so infinity is going to be come out, and that will be approximately equal to 1 over K. I will give you an example at the end of a lecture. So make sure if you have any confusion, I will just give you some description about the omega bandwidth and omega unity. We already talked in terms of gain bandwidth product previously, but again, I will reiterate the same point. But the main thing which you need for this problem is that at a DC, the closed loop gain is equal to 1 over K. And K is what? Your feedback gain. So you can find out easily 1 over K, which will be equal to 10, but K will be equal to 0.1. So you can plug K equal to 0.1 into 10 to the power 3 by whatever the number, and you can plot this phase margin of this K of S. So you can do the Bode plot of K of S, and you can figure it out your evaluation accordingly. Okay? So that's one of way to do the problem 4. You can do another ways, but that's one of the way you can do this problem 4. So let's coming back to the frequency compensation topic. So what we talk in the frequency compensation, that okay, now what happened, you have devised the system, you designed everything, and at the end of the day you find out you need to make it more stable, or you need to increase the phase margin. Phase margin needs to be increased. So what you need to do, first thing we need to understand, when we are losing on phase margin side, what does it mean? So the first and the simple thing, which I also give you analogy in the last lecture, that something instability is related to speed. Okay, at a layman, when your speed is high, you're operating at a higher frequency, this means your system is leading towards instability. So you need, if you can somehow reduce your speed, reduce the speed, operate at a lower frequency, you can make your system stable. So in circuit terms, how you can operate at a lower frequency, or in terms of that number, when this one should be less than phase crossover frequency, this is condition of stability, but we want to reduce further, or increase our phase margin further. What you should do, if your gain crossover frequency is on this side previously and your omega gx, so ultimately what you need to do, you need to bring your gain crossover frequency further on the left hand side. What it will do, if you keep the phase crossover frequency constant, so omega px constant, and bring omega gx on further on left, so what will do, it will help in making your system stable. So now how we can do this thing, the general concept of doing this thing is that this omega gx is ultimately your dominant frequency. So if you make your dominant pole move towards left hand side, or the one which is deciding your bandwidth, anyone else, to bring on the left hand side further, then it will be leading towards a system which is more stable and with a higher phase margin. So we will verify, or will do some examples to clarify this concept. So what it is provided in your book, we have an example 12.42, example 12.42. So what this do, let me draw the circuit and then I will explain what this circuit is talking about. Two stages. So we have V in being applied here. We have here NMOS, M1, M2, M3, M4, so up one are PMOSes for us. These are PMOSes, this is VDD. Here's some bias we are applying to ensure they are in saturation. And here the first stage output is connected to a PMOS here. Here again VDD. Let's call this M5. So it's a PMOS, so M5. And here we have another one, bulk biasing to ensure it's in saturation. Okay, and that somehow we are having our output at this node. So if we are given some sort of this network, and we are told that, okay, we have 3 points. This is node A, which one on the input side is node A, let's say. So we are giving this node is node A point. I will just use the red one. So here, so we have some capacitance is provided, CA. So this node is A. This node is node B, and the capacitance which is provided here is CB. So this is equivalent to parasitic capacitance, let's say. Okay, and we have another node which is ultimately output. So we have here the capacitance of CR. Okay, so we are provided these 3 nodes information, and first our task is that we need to ultimately, using our prior knowledge, we need to write the expressions for the frequencies. ठीक है, तो हम expressions अगर लिखना चाहें at node A, at node B, and at node C out. Okay. So first thing, if we are given this expression at input side, I will just point out what will be the input at this node. If we want to talk about what is my, let me, I guess there's some small mistake here. So here, this is, the first one given is capacitance here at this node, because that will not be dominant, so that we can ignore. So we are given at this is the node A between the drain and the source of M1 and M2. So node A is this. So what will be the no pole because of this capacitance CA? So if we want to write mega PA, which will be equal to capacitance CA times the impedance at this node. So if we take a lambda is equal to 0, or if not take lambda is equal to 0, even 1 over GM2 in parallel with RO1. Okay. So ultimately it will be 1 over GM2. Let's write it. And what about the pole at B location? So we have a capacitance which is CB. So let's write CB, and then we have cascode. So we know that approximate relation of the cascode GM2, RO2, RO1 in parallel with GM3, RO3, and RO4. Okay, so this is the same or prior information which we all of us know now at how to find pole that is specifically relation. So what about the output? At an output, let's write WP out is equal to 1 over C out, the capacitance as output, times. So here again we have a simple load where this RO5 in parallel with RO6. So RO5 in parallel with RO6. So this is RO6. Let's make sure. Now, if it is given to us that in the problem that CA is equal to CB is equal to C out, can we infer something about these pole locations? That which pole will be lying where, or which will be dominant and which will be not dominant? Yes, I guess we can say something about this one. If I draw the border plot based on this information, the first thing we know that if all capacitors are equal, which impedance is going to be the biggest value? The impedance which is going to be biggest value, that will be the dominant, right? Because it's inverse, so smaller value will be the dominant. So one thing we know, this is not going to be dominant. So which is cannot be dominant, I'm crossing it. This cannot be dominant. That will be the farthest one. Okay. So the pole location A will be the most far location. Among B and out, which one is going to be the most dominant? I mean, which will have a bigger value? That will be the dominant, because that inverse will come. So this is going to be the dominant one, which I'm marking with the green. That will be my dominant value. Okay. So this is the first, this is the second, and this is the third. So if you again anyone have confusion, make sure to clarify this point. So we'll start with some value until we reach the point omega PP, and then we will have something omega P out, and then we have something omega PC. Ideally omega PC a little bit might be farther from all of them. So here we start with minus 20 dB, then we will reach here minus 40 dB, and as we reach here we will go from minus 60 dB. So this is minus 20 dB per decade, minus 40 dB per decade. Again, I might not be drawing up to the scale, but you all can understand that how the things work. Okay, and this is 20 log DC gain again. Okay, so 20 log of let's not write it K, confused with the feedback ones, 20 log of whatever the value, because an open loop configuration. So let's not confuse with the same thing. So it's 20 log of A, whatever the A is, A, not A node again. Let me express with some numbers so we are clarified, we don't confuse it. So here I'm defining my Y is equal to V out over V in. So I am using it Y term here. So this is Y is here. So That's what we have, and all of us know that if we want to draw the phase one of this system, so we are going to have something. Let me draw in the next page. Again, I will draw the gain and the phase, but we need more space, might be. So just quickly draw the gain again. So we have here omega, here we have WPA, here we have WP out, and here we have WPB. Okay, so we said we start from this point, we go from minus 20 dB per decade. Let me just a little show you the less slope. So I have margin to show that, okay, there's some variation here and then here. So again, ये है minus 20 dB per decade, minus 40 dB per decade, minus 60 dB per decade. Okay. And if I draw the phase of this one, so let's draw the phase here. Again, same omega. So what will happen? 10 times less of this, it will go here, minus 45 degree. Then assuming they are far, it will continue, for example, minus 135, minus 180, minus 225, minus 270, and this like, I'm assuming they are the same. You can have this assumption. So ultimately what I'm ending at is minus 270 degree. Here at this point, minus 40. Then when they are reaching minus 90, minus 125 degree, sorry, 35 degree, minus, again, as I'm saying, might not be that much up to the scale, but that's what we need to do here. So all of the angles are going to be, and the final angle is minus 270 degree. And based on the our relation, which we know the system is not going to be stable as this. This system is not stable. Okay? Why not stable? Phase is minus 270 degree. So whenever the phase is minus 270 degree, this means it's not going to be stable. Or we know that thing if and only if we can do something with this y now. So system can be stable, but for 3-pole system, if we play around this area of minus 270 degrees, it's not going to be stable. We want our unity gain, this 0 dB path, whichever it's going to become, because we don't have the numbers here, it should come in this area where the phase crossover frequency is coming. So if this is phase crossover frequency, so we want this unity to come here. Okay, so if it's not coming here, so then this means there is something wrong. The system is not stable. So what looks like we need to do something with this system to make this system stable. But as it is, the system cannot be in a working condition. So we want like it to be early happen, meaning we want this somehow might be this pole location to go this side. So that's what we were saying. We want the dominant pole to move more towards left-hand side. If we do this thing, this what will happen. If we make the dominant pole on the left-hand side move toward near to origin, what will happen? My omega x will also go left, and omega px will be greater than omega gx. So I can achieve this thing. So I can make my system stable. How we can do this thing? By just including, for example, in this provided circuit, which was provided here, let me just rather go back to the previous one. In this circuit, if with this CB, we just add some capacitance, and that capacitance is compensation capacitance, let's say, C compensation. And now this relation not fulfill anymore, rather we have CA is equal to C out, but CB plus C compensation is bigger than CA. Okay? And because of this thing, what will happen? This omega PB, I'm drawing with the blue, will move towards left. So jitna zyada left jayega utna behtar hai. But at the cost of what? Bandwidth will go down, because that is deciding my system bandwidth. Jitna ye left side pe jayega, it's okay, but my bandwidth will go down. So I can do this thing, but I have to be careful कि वो उतनी bandwidth मुझे अगर acceptable है, it's fine. So I can have like this network. Yeah. So I can have something like this. So it's crossing now unity gain band frequency. Earlier, this means अगर हम पहले बात करें, पहले अगर मेरा system stable नहीं था, now the system is stable. So that's what we can get benefit with the help of frequency compensation. So frequency compensation help a lot in achieving these things. Okay, that's what we all need to be careful. Okay, so we can have at the capacitance and we can get benefit whatever we want, and we can just play with the thing. So in your book, you have some numbers. Make sure to add some numbers and also do some calculation. The last point, which is also related to the frequency compensation, but we talked previously in a different sense. That was frequency, that was Miller capacitance. So if I just relate the concept of Miller capacitance, you will see that somehow also related to the same point. What is Miller capacitance? So any of you just remember what we were doing in Miller capacitance? Let me just redraw that point, and then we can apply in the same circuit and see what we are doing basically. So what we were doing in Miller capacitance, we have some capacitance in between two nodes, input and output. And we said we have a gain here in, and we have C, this is compensation capacitance we called, or CF, whatever the name we gave. What was we were reiterating, okay, we can divide these capacitance into two capacitances. A remains the same, one here on this side, input side, from the node to ground, other from the node to ground. And what was the value of this capacitor? The value of this capacitor was CC times, if it's an inverting, 1 plus A. What was the value of this capacitance? CC times 1 plus 1 over A. Remember what's happening here? The capacitance increased. So instead of putting a separate capacitance, a bigger value, because that is not possible in real system, and we are going to integrate things on chip, we cannot increase the capacitance beyond certain value, because otherwise all area is going to be occupied. But this Miller give us a technique that, okay, you can have a smaller capacitance, but with this gain thing, you can bring this or mimic this a bigger capacitance. Now, whatever the A, you can have that value of the capacitance and you can make your system stable. The same thing we achieve in that configuration. Here it's not going to matter much because it's ultimately CC 1 plus 1 over A might be equal to CC. That might not be helping much, but this capacitance is explicitly adding a lot benefit to us, and that is making our system stable if it was not previously stable, or enhancing our phase margin. So the idea behind Miller capacitance was the same. So same thing if we can apply to the same circuit which we just saw. So here, instead of adding a capacitance, all of them have some VBs. VB1, here we have intermediates. So now in the intermediate, we previously adding a capacitance which was from here to ground. Why not add a capacitance in between these two stages? Kitna in dono ke darmiyan? Let me use a different color. CC. Okay. Make sure this thing should be clear to you, all of you, because that's again the same essence what we are doing. Out. Again, these are the same numbers which you said M1, M2, M3, M4, M5, and M6. Equivalent iska kya hoga? The equivalent will be, let me just draw the equivalent. In the next page, I'm drawing this, the equivalent of this network. The equivalent is going to be something like this. Again, same. V in. So equivalent is going to be, we have one capacitance. That's called C equivalent. And what's happening is going here. Now I'm just converting the Miller into two capacitances. Okay? If I'm missing something drawing here, you know, this was something similar which we just in previous two times we draw the circuit. Okay? So if this is M1, M2, M3, M4, M5, and M6. Okay? So if this is the thing, what is C equivalent? C equivalent will be equal to the value of the capacitance CC times 1 minus AV. अब AV1 आएगा, AV2, this one, which I'm marking the green. इन दोनों के दरमियान थी ना, इस point और इस point के दरमियान थी ना. So it's going to be A2. What is A2? Minus GM5 times RO5 in parallel with RO6. So just C equivalent will be equal to CC times 1 plus GM5 RO5 in parallel with RO6. So this is the C equivalent. So the capacitance of this node is enhanced by this amount, and we can easily make the system either more stable or even stable if it was not stable. So make sure this point is clear how the system is getting stable. We are ultimately bringing this thing, if previously happening this, we are bringing this like this. And because of moving this, the gain crossover frequency is happening earlier as compared to the previous. And if gain crossover frequency is happening earlier, considering that the phase crossover frequency is not changed. If omega px is the same value, same as old, and gx is lesser as compared to previously, means system is becoming more stable, or it is or our phase margin is increased, or at the same time we can say that our response is now a stable system as compared to the previous. Okay, so that is what we want to cover in the chapter 12. But before concluding, I will just give you one small relation regarding the closed loop and open loop, and then we can conclude the lecture. And after that, we will finish also chapter 12. Right. So what I'm going to talk about, it's somehow a bit might be overall summary of what we have talked about, or I feel there was something missing or some clarification which is required. So I thought might be I will cover these things, and I will also upload some related slides related to that, so you can go through, which I used to give in a different course. So with link between open loop versus closed loop. Okay. So some of the basics, why and what. So if we talk about open loop, in open loop, we have this configuration. We have input, we source, let's say, we have some source impedance, and we have something amplifier with the gain A, then we have V out. So, and we have V in here. So just make sure I'll just directly relate all the same thing. Put it down so it becomes more better. So closed loop. If I want to do a closed loop circuit, so we have an again amplifier with the gain A, same amplifier, we have V out. Now we have some feedback path based on the amplifier configuration, assuming it's a voltage to voltage. It's a resistive gain or capacitive one. So here we have now this node V in, just and the remaining things are same. The source, and we have V source. Okay. So let's make sure all of you are comfortable with these two configurations. If we want to do the Bode plot of this one, or just the frequency response to be realistic, the response will be something like this. I'm just doing the magnitude one. So we have, I will just use a different color. Yeah, if we just do this, let me use the same color, different color here, so we can identify. If we just want to do the frequency response, it would be something like this. It's a bit, again, not that much. So that's basically what is being here is minus 20 dB per decade, minus 40 dB, 40 dB per decade, and here minus 60 dB. And what it is, this point, the first one decides the bandwidth of an amplifier in open loop. So that is omega bandwidth. Then we have omega 1 and omega 2. And these omega 1 and omega 2 are normally because of the parasitics. And one thing which you can see, this is V out by V in magnitude. One thing which you can see also here, the main things, all poles are pretty much near to each other. In a closed loop in general, what we normally achieve, we have something similar, omega again. Let's use the green. So here we have something like this. Something similar which we just talked about. This is now going to be bandwidth, dominant frequency, and the parasitics are pretty much far from the your open loop. So in closed loop in general, the bandwidth in general is small. Okay, so you can see it is small. Here it's large, but here they are far. The parasitics are far. Because आपको पता है, in your system, the bandwidth, the dominant is going to be mainly the factor. If they are far, it's very good. So we want them to be far. Kyun we want them to be far? So that the system is stable. Every pole counts for minus 90 degree. And we know that the more they are far, the better it is. So in open loop in general, we want all the limiting poles to be as high in frequency, but in closed loop, we want the bandwidth one to be, or which is deciding our bandwidth to be as far, as apart from the non-dominant pole. So that's one of the rule of thumb. You need to remember this thing. Now, one important aspect which I'm going to talk now, let's assume that we have an integrator. Okay, so we have an integrator. So what is integrator for us? So integrator is somehow we have some system which S frequency response is 1 over S. Okay, a low pass filter, and we have an open loop whose response is like an integrator. So if I want to draw the circuit, instead of A of S, now I'm writing W unity by S. Okay. And I will upload some related slides to support these all arguments. Okay, so we have this one. If I want to draw the response of this one, omega here. So at this is written W unity. So this means at W unity, it's going to be something 0 dB. Okay? So it's 0 dB here plus 1, so log 10, and ideal integrator response should be going like this and continue like this. And we can call this as H of omega. So here we have this system, which is V out, H of omega, and V in. Okay? And we draw this H of omega, and we define something that H of S or H of omega is equal to W unity by S. The purpose of drawing W unity is that at this frequency is going to have a 0 dB, and we know that at omega is equal to W unity, as we just place in at this frequency, the magnitude is going to be equal to 1. ठीक है, or a unity frequency, the same. This is the unity frequency, or we can also call gain crossover frequency, WGX, जब वो उसको unity को cross कर रहा है, ठीक है. So that's one thing. Now what we want to build a feedback around this integrator. Let's build a feedback. We have h of s, which is now integrator. Now we are building a feedback. कौन सा कर रहे हैं? नॉन इन्वर्टिंग कर रहे हैं हम लोग यहाँ. So resistive नेटवर्क हो गया, Vx है, हम लोग सबको पता है किस तरह इसको निकालेंगे. All of us know now the feed forward path, जो ये है feed forward, वो तो वही का वही है. Feed forward is h of s, right? Feedback path क्या है? अगर हम k की बात करें, feedback path is formed by k. तो k क्या चीज है मेरे पास? k is equal to z1 divided by z1 plus z2. ठीक हो गया. And closed loop transfer function क्या हो जाएगा? V out by V in equal to, we all know same thing, h of s divided by 1 plus k time h of s. ठीक है. Or we can write h of s divided by 1 plus z1 divided by z1 plus z2 h of s. Yeah, you can write easily this expression for a non-inverting configuration. Now अब आता है कि because of this feedback, how my frequency response is changing. So I'm drawing in the blue the open loop configuration. So open loop configuration इस तरह की थी मेरे पास. ये omega था. So here where the point it was touching, let's, ये उसका पहले था, rather इस तरह नहीं करते, rather 1 second, yeah, just to clarify this thing. So the point where it was touching, this was 0 dB last time for us, ठीक है. So ये वाला point था W unity. Now because of this the closed loop, what's happening that I am going to have a value which is equivalent to this one for the closed loop of 20, if it's a dB scale, 20 log of what? 1 over k. Pehle it was infinity at s is equal to 0. Now it's 20 log of k, and at higher frequency it's going to behave like the same thing. So now this is the black one, is a response of mine. Black is a response of closed loop, where the blue one is open loop. So what we can conclude here, that my system is behaving as a 1 over d's, 1 over feedback at a lower frequency, meaning for s is equal to 0, the overall system V out, for s is equal to 0, the V out by V in is behaving like what? My V out over V in when s is equal to 0 is behaving like 1 over k. जो मैंने start में बात की थी कि it's inverse of the feedback. I will just put some numbers and will show you this thing. And at s is equal to very much higher value, how it's behaving. V out over V in at higher value of s, at m magnitude at s higher value, infinity for example, is behaving as h of s. वो open loop के तौर पे act कर रहा है. That is very much interesting. How? Let's put some numbers and see. So V out over V in क्या था मेरे पास? V out over V in was equal to h of s divided by 1 plus k times h of s. ठीक है. Now at s is equal to 0 क्या होगा? at S is equal to 0, V out by V in at S is equal to 0 at DC, what will be H of 0? That's something interesting. 1 plus K times H of 0. ये इंटीग्रेटर था. At 0, what's happening? This is becoming infinity. We have 1 over S. 1 over 0 becomes infinite. So at H of 0, it becomes infinite. So we can easily take H of 0 common from the numerator and denominator. So it's going to be 1 over H of 0 plus K. Okay, cancelled out. Now plus in infinity, 1 divided by 1 over infinity plus K equal to 1 over 0 plus K equal to 1 over K. So that what we concluded, that the closed loop V out by V in at lower frequency or when S is equal to 0 is equal to 1 over K. That's why whenever the closed loop DC gain is given, we can equate or approximate it equal to 1 over feedback gain. So हम लोग ये कर सकते हैं. That's one thing. Second thing, at S which is equal to 1 over plus, let me read it. Yeah. When S is infinity, what is V out over V in? At S infinity क्या हो जाएगा? H of infinity क्या है? Almost 0. ऐसे ही हो रहा है. It's becoming almost 0. So what we can do, we can get rid of some of the things. And what are those some of the things? Or it's becoming very much smaller. That's to be true. It's at K H of S is becoming very much smaller than 1. So we can write it equal to H of S. So approximately this one becoming H of the blue one is the closed loop, the red one is the open loop. And that's very much important thing which we use as a gain bandwidth product, that our for lower frequency and higher frequency. Low frequency when S is equal to 0 or a DC value, V out by V in equal to 1 over K, and higher frequency V out over V in equal to H of S. Magnitude की बात कर रहे हैं. ठीक है, that's one thing. Second thing, the general observation which we figure it out, that W unity is equal to or approximately, let's say, equal to 1 over K times omega bandwidth. अब omega bandwidth क्या है? ये some closed loop bandwidth होगी हमारे पास. Closed loop bandwidth. ये क्या चीज है मेरे पास? This is equal to K is equal to feedback gain. Okay. That's also one of the important things which we can directly utilize, that whenever we have a Bode plot of an open loop, okay, and we have the information that, okay, we know that this is my W unity. And if I draw my closed loop feedback, wherever it is touching or intersects the open loop, then that point is going to be my W bandwidth. You can verify this thing by drawing the KA. Now here, your red one is basically just H of S plot. It's not the one A times K times H of S. We can just directly use the same plot which we have figured it out in the open loop, and just draw the line of the DC gain, that because this is 1 over K is equal to DC gain. Okay, we draw the line of the DC gain and see where it touches the open loop configuration. Wherever it touches the open loop configuration and where it intersects the omega or x-axis, that will be your bandwidth or a closed loop bandwidth. So that's also, you can figure it out in problem 5. You can find out both the things using the loop gain configuration, using the loop gain, and also by this technique, or you want to verify, you want to check this thing. But this is very much important concept. What happened in the low frequency, what happened in the high frequency, definitely it's approximation, but it works, and we normally use in this configuration. Okay? So if you have any confusion, concern, make sure to update us. And that concludes basically chapter 12. And we will send an announcement for some quiz related to this feedback, because the feedback is very much important concept, and especially the stability, because like we want feedback, all system has to have feedback, and what is the main property of the feedback is the stability. So that's why if you have any concern, question, make sure to come to office hours and conclude or get all clarification. And thank you very much for your attention.